All right, let's get started. So we're going to today finish up the last two sections of chapter 3. So let's pray. Dear Heavenly Father, thank you so much for today. Please help everyone to be able to understand these words and allow them to be clear and be able to visualize the concepts from today. In Jesus' name I pray, amen. All right, so we're going to talk about conformations of ethane specifically and conformation for other alkanes. So we already talked about configurational isomers. Now we're going to talk about conformations in reference to stereochemistry. All right. And so stereochemistry represents a branch of chemistry that is concerned with the three-dimensional aspects of molecules. Okay. So we're looking at it as a three-dimensional structure taking up three-dimensional space. So sigma bonds are cylindrically symmetrical, okay? So sigma bonds, as you can see in these pictures, they're going to be symmetrical, okay? And let me make sure I get rid of this. Here we go. Because of that, rotation is possible around the carbon-carbon bonds in open chain molecules. And so that means that this bond right here can rotate. And so what I did today is I'm going to actually show you guys some 3D models of what that looks like, okay? So let's move to another window. I'm going to share that. All right, so this right here is ethane, okay? And you see how there's a single bond here? Well, let me make this smaller so you can see this bigger. So there's a single bond. And so you can actually, so we could rotate this. This is able to be rotated. Let's see. Let's see. Okay, here we go. Put this back up so you can see that. All right, so this bond, I think they want me to rotate this one, yeah. So this bond is able to be rotated around. Okay, you see that? Freedom of rotation. And because of this freedom of rotation, okay, you can have different conformations that we're going to talk about. So let's talk about this rotation again. All right. You see, as we're rotating it around, you see how it can change how it looks. Okay. All right. So let's now go back. All right. So different arrangements of atoms resulting from bond rotation are conformations. So conformations are the arrangements that are possible based on bond rotation. So nothing's breaking. All right. Remember in configuration, bonds were breaking. In conformations, they do not break. Okay. And these are called conformational isomers. These can be represented in two ways. You can see them in the sawhorse representation or the Newman projection, which is the one that we're going to focus on the most. Okay. So with the Newman projection, you're looking at the carbon straight on. So again, let me go back to make sure you guys are able to visualize that. Okay. Make sure everything is aligned properly. All right. So with Newman projection, you're looking at it like this. So see how this is like that? You're looking at it this way. And so you have a front carbon and you have a back carbon, okay? A front carbon and a back carbon. And so here, let's say that the green is your front carbon. So what you do is you want to be able to represent both the front and the back. And obviously, if you're looking at it straight on, you can't see the back carbon, but we want to be able to represent it. So the front carbon you draw as a small dot, and then the back carbon, you draw it larger circle. So that circle right here represents the back carbon, and the dot represents the front carbon. Okay, so again, this right here is the back carbon, and then this carbon right here is the front one. And then what you're going to do is you're going to put the hydrogens on attaching them to the carbon that they represent. So this front carbon has one hydrogen at top going up. So you have that hydrogen going up, and then you have the hydrogen going to each side, hydrogen going to each side. And then the back carbon, you see how you have that hydrogen going down in this conformation? That hydrogen is going down over here with the Newton projection. And then the two that are up adhere to this. All right, so you're able to see what this compound looks like in a three-dimensional setting. And I won't ignore this one. It's the same thing with the sawhorse, how you can see those going up, these are going up, and then kind of how these are going here, these are going here and down. Okay. All right. So because the compound can rotate, you have to take in consideration different types of strain. And so we're going to talk about torsional strain first. So this is strain in a molecule caused by electron repulsion between the eclipsed bonds. And so when the bonds are eclipsing from each other, you have what we call torsional strain. This is perfectly free rotation. This is a reason why perfectly free rotation is not observed. There is a barrier to rotation, and some conformations are more stable than others. So you have two types of conformations that we're going to talk about first. We have the staggered conformation, which is going to be the most stable because the bonds are as far away as possible. And then you have the eclipse conformation, which is least stable. All 6 carbon-hydrogen bonds are as close as possible to each other. All right, so let's look at this here. When the compound, all right, when we're looking at ethane, the hydrogen bonds, when they're eclipsing each other, now technically they're right on top of each other, but again, we write them slightly to the side because we want to be able to see them all. If they're right on top of each other, technically you wouldn't be able to see them. So we just write them slightly to the side. But this is when you're at the highest energy level because all 6 of these bonds are as close as each other as possible. And so if you notice in this diagram, this energy diagram, for potential energy, the energy is the highest. And then when they become eclipsed, the energy is decreased. And then as it rotates and it becomes, when it becomes staggered, it's decreased. And then as it continues to rotate, they go in front of each other again and it increases, and then decreases and increases as it rotates a total 360. Now, I'm going to show you guys what this looks like in the other window, just to make sure you guys really got it. All right, so again, right now our molecules are in the staggered position. But if they rotate, let's get them to rotate. Once they become eclipsed, that's high energy. And then they keep on rotating and they become staggered again, that's low energy. And they rotate again, energy is increasing until it's maxed out at eclipsed. And then it keeps rotating until it's now staggered. And then it keeps rotating until it's eclipsed. And then it ultimately does a whole 360-degree turn as it's continuing to turn, moving from staggered to eclipse. And so you're seeing that high, low, high, low, high, low as it's rotating. All right. Now, these values can actually be quantified. So eclipse conformation of propane has 3 interactions, 2 ethane type carbon hydrogen interactions and 1 hydrogen methyl interaction. And so because there's a methyl group on here, sometimes, so when you have it staggered, it's all fine. But then sometimes the methyl group is eclipsing with the hydrogen on the other carbon, and then you have your hydrogens eclipsing. So there's different energy levels, kilojoules per mole, based on what type of interactions. And as you can see, the methyl hydrogen, because the methyl group is larger, as you see here, is going to have higher energy than when 2 hydrogens are eclipsing each other. Now, conformational situations are definitely more complex for larger alkanes, and we're not going to go into compounds that are too large, but not all staggered conformations have the same energy, okay? So that's important to know. And not all eclipse conformations have the same energy. You have different other types of conformations besides staggered and eclipse. You have something called anti-conformation, and this is a geometric arrangement around a carbon-carbon single bond in which the 2 largest constituents are 180 degrees apart. And so let's look at what that looks like. So when your 2 largest groups, all right, are furthest away as possible, they're anti to each other. This is called the anti-staggered conformation. So when the 2 largest groups are furthest away possible, so one's at the bottom and one's at the top, or one's on one side and the one's on the other side, so it's 180 degree, right? This is the most stable conformation possible. Now if it rotates and they become eclipse, notice that this methyl group is eclipsed with this hydrogen, and this methyl group is eclipsed to this hydrogen. Now let's talk about some values, okay? These values, when a hydrogen is eclipsed with a methyl group, is 60 kilojoules per mole. And so we have 6.0 kilojoules per mole. And so you have 6.0 here, you have another 6.0 here, and then hydrogen, that's 4.0, okay? So if you add this all together, you have a total of 16 kilojoules per mole. So let's look at some other scenarios to see if that can change. But before we go to the other eclipse, let's talk about one more staggered. So after this rotates, what's going to happen is this time, while here, your 2 largest groups were anti to each other, now this time, even though it's staggered, your 2 largest groups are actually directly next to each other. When they're directly next to each other, that's called the gauche conformation, or gauche conformation, okay? And even though these are staggered, there's still a little bit of strain. Now, it's not torsional strain, but it's called steric strain, okay? And so this is based on the molecules being so close that they're crowding each other. So there's some energy that is needed for that. And so when 2 methyl groups are gauche conformation, that energy is 3.8 kilojoules per mole. So as you see, it's not as much as if it's eclipsed, but it's still a significant amount of energy. All right, so let's talk a little bit more about steric strain. This is the repulsion interaction that occurs when atoms are forced closer together than their atomic radii allow. So as I said, it's based on them being too crowded, okay? So here you see that you have strain because these groups are too large. Now with the hydrogen-hydrogen interactions, there's no strain there, okay? Neither torsional nor steric. So you don't have to account for that. The only thing you have to account for are these 2 methyl groups. So the total energy of this staggered conformation is 3.8 kilojoules per mole. Now if you rotate this, you now have a eclipse conformation, and it's the highest energy eclipse conformation because not only is it eclipsed, but the 2 methyl groups are eclipsed with each other. And so this is going to have torsional and steric strain. And with both of those strains together, you're going to have, instead of just 6 kilojoules per mole, it's going to be a whopping 11 kilojoules per mole. And so if you're going to add up all of this, you have 11 plus the 2 4s from the hydrogens that are having torsional strain to give you a total of 19 kilojoules per mole. So you can see that this conformation has the highest energy. So let's look at it here. So you have anti, which there's no torsional or steric strain, so it's going to have the lowest energy level. And then as it rotates, you're going to have the eclipse of the carbon from the methyl groups, right? And the hydrogens would give you the 16 that we saw. Then as it rotates again, you now have the gauche conformation. And so you're able to see that 3.8 is still not as less or as little as the anti, but it's still pretty low. And then it goes back up a lot higher when you have your eclipse of your 2 largest groups. And then it comes back down to gauche again as it's rotating. You can see that the front carbon is staying still and the back carbon is rotating by 6 degrees every time. And so then you have gauche, like I said, and then it rotates and you have eclipse again. But again, this eclipse is only going to be 16 kilojoules per mole because it's just the hydrogens, it's not the methyl groups. And then you get back to the anti, which is going to have your lowest energy. All right. So you're going to want to know how to draw these. And so what you would do is you would calculate them first. After you calculate them, you would then draw the different conformations. So here's a table of the different energy costs. And so you have your hydrogen eclipse torsional strain, which is 4 kilojoules per mole. And we're going to stick with these numbers here. And then you have your hydrogen methyl eclipse, which is mostly torsional strain. And so you have 6.0. Then you have your methyl eclipse, which is torsional and steric strain, like we talked about, to that 11. And then, of course, you have your gauche methyl interaction, which is going to give you that steric strain there. Now, let's do some drawings. So side along the C2-C3 bond of 2,3-dimethylbutane. So let's first talk about how to draw 2,3-dimethylbutane. So let's listen to the name. So this is a butane. And so butane is going to have how many carbons? That is 4. And then you have 2,3-dimethyl. So that's 2 methyl groups, one on the 2 and one on the 3. Okay, so here's your structure. It's asking for a Newman projection of the most stable conformation upon the 2,3 sight line. So if I have my 2 and my 3, I'm going to draw a dot for 2, a circle for 3. And if I'm looking here, I have a CH3 up here going straight up. And then I have my 1, which is going to go here. So I have a CH3, CH3. And then it's not drawn, but there's also a hydrogen here, right? So let's put the hydrogen here. And then in the back, I have a CH3 going down. Okay. I also have a CH3 that if I'm looking this way, we're going to say it's going here. I have a hydrogen on that that's also here. Okay. So now I want to draw the most stable conformation. All right. So if you notice, the first thing is, of course, it's going to have to be staggered. So automatically, you know, you're going to have 1 up and then the other one down. Then as you're putting your methyl groups, you want to make sure that your methyl groups are as far away as possible from each other. With that being said, because you have two sets, there's not much you can do, okay? If you just had one set, then you would take in consideration that. All right, so again, this conformation is the most stable because it is staggered. So guess what? We're at the end of the chapter and we're doing a summary. Now, even though we're at the end of the chapter, there's a lot of practice and a lot of things that you can do when you're dealing with your staggered and eclipsed. So definitely need to do some practice problems in the book. And so look out for those questions for chapters 1, 2, and 3. But let's go through the summary. So this chapter, we looked about how to group of atoms within a larger molecule that has characteristics chemically reactivity is called a functional group. So a group of atoms that are arranged a certain way is called a functional group. Chemical reactions of an organic molecule are determined by its functional groups, all right? So the functional groups is what gives the chemical reactions the characteristics of your molecules. Now, alkanes are classed as saturated hydrocarbons, and alkanes don't contain any functional groups, are relatively inert, and can be either straight-chained or branched, okay? So if you have a true alkane, you're not going to have any functional groups, just simply a hydrocarbon, okay? And these could be either straight-chained or branched. Now, we have constitutional isomers. These are compounds that have the same chemical formula, but the structures are different. And so that means bonds are broken and turned and changed to create different connectivity, even though the molecular formula is the same. Now, rotation is possible around the sigma bonds because of their cylindrical symmetry. All right. And so there is rotation that is possible that we just talked about. Also, alkanes exist in a large number of rapidly interconverting conformations. And so these alkanes can twist and turn, and they're just ever rapidly changing. Now, newer projections that we just talked about make it possible to visualize these spatial consequences of bond rotation. So we're able to use this model to be able to evaluate what is happening as the bonds rotate. And we know that staggered conformation of ethane is 12 kilojoules per mole and are more stable than the eclipse conformations because of torsional strain, okay? And so staggered conformations are definitely more stable than eclipse. So generally, all alkanes are most stable when all of its bonds are staggered. All right, don't forget that. Generally speaking, alkanes are most stable when all of their bonds are staggered. That's going to mean a lot when we talk about next chapter in chapter 4. So let's not forget about what we learned about infrared spectroscopy. Infrared spectroscopy identifies functional groups in a molecule using electromagnetic radiation in the infrared area. Okay, organic molecules absorb a certain frequency from electromagnetic radiation, and that frequency, when it's matched, causes vibration, which is what gives us our configuration. And again, that is it, you guys. We made it. We have finished chapters 1, 2, 3, and part of chapter 12. You guys are doing awesome. I want you guys to take this time after you watch these videos between now and our next set, after a short pause, to be able to do some practice problems. So get these videos done so that we can do those practice problems. All right, until next time, I will see you later.